Okay, like this. Okay, and I should turn off. How do we turn off the recording? No, no, no. I just because yesterday I think it went on forever. I didn't. Ah, they will cut it. Okay, okay, okay. Thank you. Okay. Okay. All right. So we can start. Are we all in? Okay. Okay. So we start. Tomorrow we start at 11:15. Okay. So tomorrow 11:15, and on Friday at 9:15 we do a shift in time. So a brief recap of what we've seen yesterday. So we begin talking about the interplay of locality, no? So symmetries, topological operators, and locality, where the fact that symmetries are locality preserving was essentially highlighted as the defining properties of symmetries of quantum fields. Okay. And then, and then we declared our intention of studying the interplay of this with the RG flow, no? And then, before diving into details, we started an heuristic argument about what structure do we expect symmetries to have, no? So we have a heuristic argument about what structures to expect. Okay. In the heuristic argument, I was going a bit too fast because my hope was to be able to finish in 1 hour, but it was like wishful thinking. So today we take it back from here, no? And hopefully, going a bit slower, I will be able to cover the whole thing in the first hour. And then the plan is to continue in part 2, the second chapter, with a study of symmetries in 2D CFT. No? This is the next argument. So right now we go back to the heuristic argument. No? So at least one thing I hope you remember is that there is this idea that belief that global symmetries are an emergent phenomenon. No? As we decouple gravity. And we land in an effective field theory description. No? So we argued using black hole thermodynamics more or less gave us an heuristic argument to expect that there is a scale of symmetry breaking that happens a little bit below the Planck scale. No? And our field theory description will live here, no, in energy below this scale. No? So this is something that we discussed yesterday. And then what we started looking at were field theories that we could get. And the idea is that consider the symmetries that we can obtain from this process inductively in the dimensionality of space-time. So starting from d equal to 1 plus 1. No? So in this dimension, in d equal to 1 plus 1, we say that all excitations are particles. No? And therefore have word lines. No? And upon decoupling, we have identified 3 different behaviors. No? So the energy cost for displacing these word lines can be infinite, finite, or 0. No? And the quantum mechanics governing it can be gapped or not. No? In particular, we say that the one that have require an infinite energy to displace, they correspond to defects or impurities in the quantum field. I stress, these are not topological, non-topological, non-topological. So inserting one of these lines that require an infinite amount of energy to move is really something that changes drastically the structure of our quantum field. We are studying the quantum field in presence of an impurity, a spurious, spurious part of space-time. It's like, I don't know, you can also think of it by removing a part of space-time and prescribing boundary conditions around it, say. So these are these defects. And the one that instead require 0 energies and are gapped, these are the ones that we want to identify with the symmetries. Okay, so these are the topological operators. Okay, that we end up with. Okay. So the ones that are finite energy, these are typically the ones that are associated to excitations of the quantum field that we obtain. No? These are the dynamical excitations. No? So we end up with a field with impurities, operators describing excitations, and a collection of topological lines. Okay. So the operators, so we insert them in space-time, no? So we insert an operator in space-time at a point, no? And so if we have a topological line, we can consider surrounding this operator by our topological line. We will call them D, okay? And in this way, inducing an action of the topological line on the operator, no? So since we can essentially shrink these topological lines to zero size, we can get an identification with this, and say if you want an action of the line on the operator, no? Just by shrinking it. This is more or less the way in which we want to encode symmetries in this way. Of course, like there is a trivial line, no? There is which is a transparent line. It just corresponds to the identity transformation in this business. No? Just that doesn't do anything on anything, and it doesn't support any degree of freedom. No. So what we want to do now, so is to see what we started to do yesterday, was to start trying to understand what is the structure that these topological lines end up having, just from this decoupling perspective. No? And in particular, so we want to claim, no, the claim is that these DIs, no, will become the objects of the symmetry category. But what are the morphisms? No? I told you, no, a category is just a collection of objects and a collection of maps between them. Okay, this is how we want to think about it for this, for the time being. No. So what are the maps that we have between these topological lines? So the morphisms arise from topological operators that we can insert along the lines that transform them one another. No? These are like line changing operators. And since these have a quantum mechanical origin from our decoupling perspective, we expect that these line changing operators will inherit by decoupling the structure of a complex vector space. No? After all, these are operators in quantum mechanics, and we know that operators in quantum mechanics belong to a complex vector space. No? So we have a category that has as objects the lines, and the morphisms are complex. The morphism spaces have the structure of complex vector spaces. Okay. Well, just to give an intuition for the physicists, because the fact that on these word lines live quantum mechanics, that's something that follows from this perspective, if you like. No, we're just doing this heuristic argument. No, our starting point is that we obtain these lines from somewhere. No, and this somewhere is this decoupling from a more fundamental theory where we integrate out gravity, no? And we end up with an effective field theory description. Of course, if you start directly in field theory, it's also like this will also happen, no? But just for the sake of the heuristic argument, this is what we want. No? So in particular, no, in particular, in particular, if we consider the morphisms from a topological line to itself, which typically is called the endomorphism space, this will be just the symmetry of that quantum mechanics. No? The vector of these local operators on the quantum mechanics. No? So, in particular, we get that the category therefore has a linear structure. No? So we end up with a category of this kind. Are said to have a linear structure. Then last time I started discussing the fact that there is more that we can do with these lines. No, there is of course we can end them on points, no, and we can also I mean we can form more complicated junctions of lines. No? In this case, we will have an operator which is labeled by 3 lines. No? And on top of that, we mentioned the fact that we can also fuse them, since they depend only topologically on their support. We can fuse them. So in particular, the idea is that you have lines that are parallel to one another, and you just bring them together. No? And since this is a superposition of quantum mechanics, we know that the outcome will be given by the tensor product of the corresponding quantum mechanics. No? Yes.
Characteristics of this high setup is C linear structure. Is the you're saying the inherent complex vector structure?
Yes. So the C-linear structure is the fact that the morphism are vector spaces with complex coefficients. No? On top of that, on top of the C-linear structure, no, we have also this fusion operation. No? This fusion operation from our perspective of physics is very natural. We just take 2 lines, they are topological, we bring in one on top of the other. No? And we know what happens when we tensor them, because we get a tensor product of Hilbert spaces. No? But there is an interplay between these operations and the morphism spaces, precisely because of the topologicalness of the structure. So for instance, if you have just 2 lines that come together at a point, no? You can consider an operator that is implementing this superposition. So a category of this type, a category that has a tensor product operation, is said to have a monoidal structure. So just the statement that you have this product. No? And it is interesting to remark that this category will also have objects that are so-called simple, which corresponds to, to IR fixed points of quantum mechanics with a single ground state. So the endomorphism in that case will just be isomorphic to C, because it's a single ground state, so that the space of operator is just a copy of the complex numbers. No? Yes? Mm-hmm. Yeah, you just you just do it, no? Like that operator is inserted at this junction. You take another one, is also inserted at the junction, and you can define their sum at the same junction, exactly, no? Accordingly, no? And if you want to multiply it by a scalar, you just multiply it at a scalar and you insert it. No? Like they inherit the structure of the operator algebra. Yes. Ah, this one is a good question. This one is a specific example of that, where decay happens to be the tensor product of 1 and 2. No? No. Yeah, in general, no. In general, this thing is you can think it in many ways. This thing, for instance, you can think of it as if it is a morphism between di tensor dj into decay, no? But also di tensor decay into dj. There can be orientation data, no? So yes, like I see the point. Yes, the tensor branches. Yes, exactly. Yes, I think so. Yes. Yes, but the way in which you see it as a tensor product, there are many different ways in which you can see it as a tensor product, no? And that will give rise to spaces that in principle are different, no? And that correspond to possible different fusion channels, no? But we will see it in detail when we study 2D CFTs. Precisely this structure will arise there. And exploiting the fact that CFTs are more constrained, we will be able to say more about this and compute it more in detail, no? So, yes. Just think about it. No, so we have this category. No, the category has the objects and the maps. No, but now the fact that it comes from this construction entails that this category has more stuff. No, one thing that we notice is that the morphism space are C-linear vector spaces. Another thing is that it has this product. No, this product is extra data. No, is something that indeed takes two objects and assign another object. No, and that the existence of this product on the object is the monoidal structure. Does it? Okay. Mm-hmm. Yes. Very good question. Yes, indeed. No? The fusion product of lines is associative. No? No? But the associativity of the product is captured by an interface. Let's call it F, and then D1, D2, and D3. And this one is an element in the morphisms of D1 tensor D2 tensor D3 into D1 tensor D2 tensor D3. So in general, it's not a trivial operation. And how do we construct this morphism? We expect to find a line-changing operator of this type. No? So this is a diagram that I drew last time, but I was probably too quick. No? So you see, say that this is D1 tensor D2 tensor D3. This is D1 and D2, and this is D3. Sorry, D1 is on the bottom. This is D3. Okay. So D2 and D3 come together before, and then we bring in D1. No? And then we can consider performing the same fusion, but in the different order. No? And you see, all of these lines are topological. No? So this bubble that we have formed by performing this operation in two different order can be shrunk to a point. And this point is what we call the F. Interface. No? And now, because of the topological nature of these junctions of topological lines, the associator morphism has to satisfy some sort of a pentagon identity. So which is essentially associated to a commutative diagram. So the idea is that you consider the fusion of 4 objects. No? And you consider performing these F operations. No? So for instance, here I'm performing it on this, on the product of these 3, on D2, D3, D4, and I'm swapping their order. No? No? Now we are working with these three objects, and we obtain this identity. And now we are doing it on this part. But we can also go another route. And exchange, work with these 3 elements. And then go back here by this operation. And you see, since all these manipulations are topological, they just correspond to inserting these topological interfaces, this diagram has to be commutative by construction. No? And this gives a relation where we have 3 F symbols and 2 F symbols that come together and have to give rise to a consistent composition. No? So this is why this is called the pentagon. The pentagon identity, because it is an identity that involves 5 F symbols. Okay. So on top of this, okay, we have this, this trivial line, which I mentioned before. And if you have a bilinear monoidal category that also has this, this trivial line, no? You can ask yourself whether the category has evaluation and co-evaluation maps, which are, from our perspective, are processes that are associated to folding the line over itself. No, we have this topological line. We can consider folding it over itself. No? And this will give rise to a morphism, if you like, that takes d tensor d bar, where d bar is just the orientation reversal. Into the identity. And similarly, we can do it in the opposite way, no? From our perspective, from the perspective of decoupling, this corresponds to creation and annihilation of these word lines, no? So we expect to have them, and these mappings, these morphisms are called evaluation and co-evaluation. No? So by construction, we know that there is an inverse, there is this orientation, there is an opposite line for every line. This if you want, is a consequence of the CPT theorem. No? There is an orientation reversal, there is an opposite line. And for each opposite line, we have evaluation and co-evaluation maps. And so if you have a category of this type, no, that has this additional structure, so the fusion operation, this evaluation and co-evaluation maps, an associator that satisfies the pentagon identity, then you satisfy the axiom of a tensor category, it's called. Okay, so our lines, essentially by construction, just by playing with them thinking about what we can do with them, exploiting their topological nature, they satisfy the axiom of a tensor category. And so we can use the theory of tensor category to speak about them. No? Moreover, if you by chance consider a finite collection of topological lines, then the category becomes a fusion. No? So if it is finite, then you obtain a fusion category. Okay? And this can happen in many cases. So particularly, we will see in the Ising model, we will have a fusion category as a symmetry. So to relate this with the context of ordinary symmetries, no? You have to think that in those examples, if you work with a two-dimensional theory that has a symmetry group, no? Then the group elements label your topological lines, no? So to relate them with ordinary symmetries, you think about the group elements, which are the topological lines, are labeled by group elements, no? You have something like this. And these fusion channels are always one-dimensional, no? Correct. So in the way I'm constructing it in this heuristic argument, I'm, con I'm considering as objects of the symmetry category the symmetry generators, no? But from a more mature perspective, it is more natural to consider as objects of the symmetry category the quantum field theory itself, and as morphism the topological interfaces between different quantum field theories, no? So, since you asked, let me make this remark, no? For this heuristic argument, no? But one second, let me finish. But from a mature, but to consider a category that has as objects d-dimensional quantum field theories and as morphisms topological interfaces between them, no? So the idea is that you would like to consider two theories equivalent if there is a topological interface that separates them, no? And then from this perspective, the category that we are constructing is essentially the endomorphism category of the trivial interface of a given object of this extended symmetry category, no? So this would be the single object in this case, and these ones would be the morphisms. Okay, this is just to relate to that remark. You had a question? Yes. No, you can think of them literally as being, so the group is just a a parameter, if you like, of the possible topological lines. No? And the way in which they act on operators, that is what gives rise to the representations. No? So when they wrap a point-like operator and they transform it, they will transform it in a representation. Yes. Topological interfaces. Interfaces. An interface is a so say is like a membrane that separates two regions, no? Two regions, no? So you have your field theory in one field theory in one field theory in another, and there is an interface between them, no? If the interface is topological, then from this perspective you can think of it as if it is a morphism, no? And what we are doing now is we are constructing just the topological interfaces of a given theory with itself, no? Yes.
Kind of interface, is it in space-time or is it in theory?
It's in space-time. Yes.
Consider quantum field theory on one side of the
And another quantum field theory on the other, yes. Or you can also consider defects, topological defects that fill the whole of space-time and map one theory to another one, and those would be the -1 form symmetry generators that I mentioned yesterday, no? But for the sake of clarity, I prefer to work with this. So we will stick to this for these lectures. Okay. Mm-hmm. Mm-hmm. Eh, I don't. You shouldn't write equal in this context, because if you want to write equal, you should specify a lot of data. No, you should specify where these defects are inserted. No, how do they come together? No, and these data we don't care about because they are topological. No, and so what we mean by the associativity is that there exists a morphism between one and the other, one order and the other. No? And the fact that there is a morphism means that there is a topological interface, and that one is something that we can wiggle around. No? It establishes an equivalence between the two, no? But this equivalence might be non-trivial. No? Okay. Exactly, yes. Exactly. It's a bit more like it kind of encapsulates the whole thing. No? So oftentimes instead of writing equal signs in this business, we write arrows. No? But you can think of them as if they are equal signs. From the physics perspective, they are like kind of equal signs. No? But they are really isomorphisms. No? Um, and I don't know if I will have time to cover this, but the idea is that if you start with this construction and you plug it into the associativity diagram that I drew, you will recover that there is more data than just the data of the group that correspond to the associator. But we will go over it, I think, in the discussion of 2D CFTs. Yes. So yes, if you like, no. So this would be this would be just the trivial identity operator, no, that fills space-time, no. And so that's when you study the symmetry categories we are constructing now, no, is just this one, is the endomorphism of this object. We work with a fixed theory, no. We are not considering interfaces, but that's just because of how I constructed the heuristic argument. No? In general, you can think of this. No? So now, so we've seen. So the outcome of this is that for d equal to 1 plus 1, no, the symmetry will satisfy this axiom. We expect the symmetry satisfies these axioms. No, it's the axioms of a tensor category, and if the collection of topological lines is finite, then what we end up with is a fusion category. Okay. We expect a fusion category, no? Now, what happens in higher dimensions, no? So, in that case, you see, the decoupling argument give us a more rich story, no? In higher dimensions, we have a more rich story. No? Because we don't have only particles, no? We have particle-like excitations that have word lines, but we also have strings, for instance. And they will have word sheets. And in general, membranes. That will have word volumes. No? And these are all ingredients that we are familiar with in quantum gravitational theories of gravity. No? And in the decoupling argument, to all of these higher dimensional configurations, we can run them through the same classification that we considered before. No? So all of these, all of them, we can, upon decoupling, organize according to the energy cost of their displacement. And whether their word volume theories are gapped or gapless. No? So again, if the cost to displacing them is zero, is finite, or is infinite, we will end up with some topological operators and with some defects or impurities. And we will also end up with some excitations. No? But now all of these gadgets will have different dimensionalities. According to whether you start with a particle, a string, or a membrane. No? And so we expect to end up with something that has excitations and topological defects, topological operators of different dimensionality. And they can have this more intricate interplay. No? So notice that in this case, since we are in higher dimension, the behavior of the word volume theories upon decoupling has a more interesting dynamics. No? In particular, you can have instances where you flow and you end up with some defects that support some conformal degrees of freedom. No? And this gives rise to a very interesting dynamical system where you consider the scattering uh, excitations in the bulk of your field theory against the defect. There might be some energy exchange, but we won't consider this case in the heuristic argument. We will just stick to the case where we end up with a collection of topological operators, and on the topological operators we have gapped theories. Okay. Otherwise, we end up with a system that is more complicated. It's not just a genuine quantum field theory in the dimensions. It is an interacting system where we are considering quantum field theories in different dimensionalities that talk to each other. It's like in conformal field theories, they're called defect CFTs, for instance, and they're an interesting subject, and will have richer symmetry structures than the one that we are considering now. No? So, how do we organize this? But I just wanted to mention that this is something that can happen. So how do we want to organize the object of this symmetry category? No. The idea is that the objects, if we stick to this interpretation where we stay in a given fixed field theory, no, they will be the topological membranes of lowest possible codimension. No? So in 2 dimensions, they were lines. No? But in d dimensions, we expect to have a d minus 1 dimensional membrane, topological membrane. No? Eh? They will also be there. No? They will also be there, but they won't be objects. So we've seen, no, that in d equal to 1 plus 1, the objects were lines, and the morphism were these line changing operators. No? Now, in greater dimensionality, the objects are in codimension 1, no? Like, in this case, let me draw in 3 dimensions, they would be like surfaces, if you like. And the morphisms between them, they would correspond to topological lines. No? So the morphisms are topological interfaces between them. No? But think about the case of 3 dimensions. No? No? In 3 dimensions, we know that if we have a collection of topological lines, no, they will form a one fusion category. No? They are exactly the gadgets that we just constructed in 2 dimensions. No? And so they will have their own morphisms, no? In terms of topological points. No? It can be a point operator connecting this line with another line that still give rise to an interface between these 2 surfaces. No? So there are morphisms, but there are also morphisms of morphisms. No? Because each topological interface give rise to a morphism, but if they have more dimensions, there is room to insert further topological interfaces that are smaller, and they will give rise to a higher structure, higher morphisms, they are called. No? Higher morphism. No? So just out of looking at these topological interfaces, we see that they are organized by a category with objects and morphism and higher morphism. So it is a higher category. Now, in higher dimensions, we get a higher category. No? And like one of the things that I want to convey is that we shouldn't be scared by these gadgets because we can understand them physically in terms of topological interfaces that wiggle. Okay, and these topological interfaces are very computable. No, in mathematics, the typical approach towards higher categories is very abstract. They use homotopy theory. They want structural properties. No, we are very modest field theorists, and we have a specific quantum field theory in mind, like I don't know, quantum electrodynamics. No, and there is very little space to hide there. You have your operators, you have your lines, your surfaces. You can compute explicitly all these ingredients. You can compute these interfaces. You can compute these topological operators. No? So, moreover, so let's consider one of these objects. So it's customary to label these topological defects by their codimension. No? To label a topological operator of codimension p plus 1 by dp. No? It's a bit of an uncanny convention, but the reason is that in this way you remember what is the dimensionality on which these guys have a chance to act by linking, no? Which we discussed yesterday. So in this case, we have our objects. They are the zero, no? And what is the structure of the morphisms that we expect, no? So the zero will be a d minus 1 dimensional and according to our way of organizing them, we expect to have a d minus 1 dimensional topological field theory. That lives on as a word volume, so the word volume theory. As a word volume theory for this D0, we expect to have a d minus 1 dimensional topological field theory. No? And you remember, like these were the operators in our quantum mechanics. Now this would be the symmetries, if you like, the topological operators of this topological field theory. No? So the morphism space is here. We expect the morphism spaces to behave as higher dimensional topological field theories. Operators, no? So the morphism spaces, we expect them to behave as higher dimensional topological field theory operators, no? And yes. So yes, sorry. We are thinking about the objects that we get, no? In this case, And the objects, we say they are topological membranes of smallest possible codimension. And so typically we say to label them, we can label the operators with a superscript that says what is the dimensionality, and the convention is this one, that if you have an object of codimension p+1, it's labeled like this. So D0 would be a topological membrane of codimension 1. So something that has dimensionality d-1. Okay? So this would be one of the objects of our symmetry category. No? Yes, just for the sake of simplicity. So from the mathematical literature, we expect that the operators in topological field theories are indeed organized according to a higher fusion category, whatever that is. No? And the way in which that is defined is precisely by an inductive step like the one that we are doing now. No? So we expect from this heuristic argument that in d dimensions, so in d dimensions, a symmetry category is a category enriched, it says. Enriched over fusion or tensor d-2 category. No? Where the fact that it is enriched is just a statement about the fact that the morphism spaces have the structure of a fusion or a tensor d-2 category. Okay. By the way, this is as close as you can get to a definition of a higher fusion category also in the mathematics literature. No? So it's a category whose morphism space, like in the case of fusion category. For a fusion category, it's a category whose morphism spaces are enriched over vector spaces. No? And here, what we just saw is that the morphism spaces will be enriched over a higher category that has all this fusion structure, etc., of one dimension lower. No? And in a sense, you can define these objects inductively in this way, no? By further enriching them dimension by dimension. Okay? Sorry, where are you? Because so the objects are d-1 dimensional, no? The morphisms are interfaces between d-1 dimensional topological defects, which therefore have dimensionality d-2. Exactly, no? Exactly, no? So, and the lines we saw, they have the structure of a fusion category, no? Not higher, but that's the first step, if you like, no? So they would be the morphism, and they, on their own, they have a structure of fusion category, no? So that's the example, no? So this is the end of the heuristic argument, no? Just by decoupling, no? Just by the idea that we come from a theory that is more fundamental, no? And the fact that this theory has excitations of various dimensionalities, as we expect from say, string theory or other constructions, we can deduce that the structure of topological defects that we expect in any effective field theory is that of a higher category, which is enriched over a d-2 category. Okay? In the rest of the lectures, we will explore these structures in very, very increasing levels of details, no? In the context of very specific examples of field theories. No? So up to today, this was very abstract, and my hope was to conclude this yesterday. but right now, from now on in the course, what the plan is that we will consider concrete examples of field theories, and we will learn how to compute with these tools, exploiting field theory techniques. Okay, so this is essentially a conceptual framework that we will populate with field theory concepts. Okay. Questions? We can have a break, and we can resume in 15 minutes, say 25. Okay. Technology. Okay, so let me repeat what I said so far. So we'll consider two-dimensional, for the sake of the audience online. We will focus on, now we open the second part of the course, we'll consider 2D CFTs that are unitary, local, and compact. By compact, I mean that they have a unique vacuum, a discrete spectrum on any spatial slice. In particular, we know that for this class of CFT, we expect there is a stress energy tensor, T mu nu, and it is conserved, and in particular, conformal symmetry requires that it is traceless for scale invariance. And in two dimension, we can consider the theory in Euclidean signature by a weak rotation, give complex coordinates to this plane, and these two conditions translating the fact that there are only two components of the stress tensor that we care about. One is holomorphic, one is anti-holomorphic, and out of them we can build the Virasoro generators in a standard way. You told me that you are familiar with this, and for this reason I'm going very fast. There is a standard reference that where you can find essentially all of the material that I'm presenting now. This is nice work by Ginsberg on the archive 9108-028, which I strongly recommend if you haven't seen it. It's a classic. So each collection of generators satisfies the Virasoro algebra. And out of the OPE of the stress tensor, you find that there is a central extension which gives this algebra central charge, C. No? Okay. So we have two copies, one for this and one for that. We call them Vir C and Vir C bar. Now, one feature of these theories that is very helpful when we study them is the so-called state operator correspondence. No? State operator correspondence is the statement that you can consider these theories on R2, no? And you can insert an operator at the origin, local operator inserted at the origin, and you can consider evolving the system according to dilatation, no? And this gives rise to a process of quantizing the theories that is called radial quantization. No? Where you consider as the Hamiltonian, you consider the dilatation generator, L0 plus L0 bar, no? And there is a nice conformal transformation it's the minus IW that maps this into a cylinder. Where where sigma is a coordinate, the radial coordinate of the cylinder, and the Euclidean time goes upwards, no? And W is just a sigma plus I t Euclidean, okay? And now the idea is that the operators, the local operators that you insert here, no, are mapped now to states in the Hilbert space of the theory on this circle obtained from quantizing on this cylinder. No? In particular, the identity operator here maps to the vacuum, which by assumption is unique. I will denote it either vac or 0. No? Be careful to not confuse my 0 with my O's. Now, this state operator map is very useful in studying two-dimensional CFTs because it allows us to exploit the unitarity structures and properties of states in a Hilbert space to constrain the features of the operators. So exploit state operator map towards unitarity constraints. Now you're familiar with the Virasoro algebra and 2D CFT, so you know that there is a collection of primary operators. No? This would be the L0 eigenvalue, and this is the L0 bar eigenvalue. These are primary operators. And upon this state operator map, they go to lowest weight states of Virasoro irreducible representations. So we have states corresponding to H and labeled by H and H bar, which are such that there is an N such that this is destroyed by both. No? For all the higher ones. No? Now the fact that states in the Hilbert space have positive norms states in well, maybe for all n greater than a certain n tilde is better. This n tilde is positive. States in H of S1 have positive norms. No? NH N H N okay, sorry. The state in this cylinder Hilbert space have positive norms, no? And this is what we use to get unitarity constraints, no? So in particular, from the fact that we can consider the norm of this state to be positive, follows that the central charge must be positive. States in this cylinder Hilbert space have positive norms, and therefore we get unitarity constraints. No? So for instance, requiring that the norm of this state in particular is positive, implies that C is greater than 0, and requiring that this one is positive implies that H and H bar, the conformal weights, are always greater than 0. And we can use it to study and constrain or determine the reps of the Virasoro algebra, which we will call MCH. M because they are also called Virasoro modules. Okay. Now, in particular, if the central charge is less than 1, there are so many constraints that there is a discrete set of solution. Which are the so-called minimal models. And their central charges go like this. 1 minus 6 over m times m plus 1, where m is 3, 4, 5, and so on. For m equal to 3, we get the Ising model. For m equal to 4, we get the tricritical Ising model. And so on. No? In particular, they have a discrete spectrum. Of conformal dimensions, which are parameterized by 2 integers, and have this structure. So we have m plus 1 times r minus ms, the whole thing squared, minus 1 over 4m times m plus 1, where r is less than m minus 1 and s is between 1 and r. And there are also relations between different pairs of r s and r prime s prime. So I refer you to this work by Ginsburg for the details. So in particular, if we compute it for the Ising CFT, m is equal to 3, so c is equal to a half. And if you write down the possible allowed h's, you get a table like this. R goes this way, S goes this way. You have 0, a half, 1 over 16, 1 over 16, a half, and 0. And so the allowed values for h and h bar are just in this set, 0, a half, and 1 over 16. Now, in order to understand more precisely what is the spectrum of the theory, we still need to constrain the possible degeneracies. And find if there are relations between h and h bar. No? So, and to do that, we are going to use locality. No? For that, we are going to use locality. Now, for us, in this context, locality means that we can define our field theory on any general space-time manifold and we are free to choose different special slices to quantize the theory. So remember, here we are in the Euclidean formulation. No? In particular, locality implies that the choices, these choices of quantization will not affect the observables we are interested in. No? So whenever we have a compact manifold, we can choose to slice it in different ways. And each different way we choose to slice it gives rise to a different quantization of the theory, because we are identifying a different direction as the time direction. No? But these are just choices, and it shouldn't affect the value of the observable that we are computing. No? And so we can exploit this if we have a manifold that we can slice in different ways. We can exploit this to constrain the value of the observable. No? And the modularity constraints on CFTs arise exactly in this way. So to constrain the degeneracies of the operators in the Ising CFT, we will use modularity. No? Are examples arising from considering our CFT on T2. So T2 is just C modded out by 2 pi times the integer lattice generated by z plus tau z, where so the idea is that the fundamental domain that we are using is something like this. Here is 1, here is tau, which is tau 1 plus I tau 2. No? And we can consider the partition function of our CFT on the torus with respect to this modular parameter tau and tau bar. No? And we can relate it to the cylinder circle Hilbert space picture of above. Because the idea, remember, we have our this is our tau Euclidean, this is our sigma, no? And if we do identify the top and the bottom of the cylinder, we end up with a torus, no? And so when we make the Euclidean circle into the Euclidean direction into a circle, what we are doing is we are computing a trace, no? This is a trace over our circle Hilbert space. But since we are using a torus with this modular parameter, this corresponds to having inserting an operator here, in an evolution operator like this. So this is T2 times the Hamiltonian on the cylinder, and then we have plus 2 pi I tau 1, and this is the momentum on the cylinder, no? Where the Hamiltonian on the cylinder here will be L0 plus L0 bar minus C over 12, and the momentum on the cylinder is just L0 minus L0 bar. No? 2 pi I tau 1 P cylinder. So just by using this definition and reshuffling, you see that this is also equal to the trace over this circle Hilbert space of Q to the L0 minus C over 24 and Q bar L0 minus C over 24, where Q is equal to e to the 2 pi I tau, and Q bar is equal to e to the minus 2 pi I tau bar. Okay? Yes? Z of T2. Thank you. So we can relate the two pictures. And we can exploit it to constrain further the spectrum of the theory on S1, which is what we are after. No? In particular, what do we expect? So we expect a positivity and integrality constraint, which is a statement that this T2 partition function has a decomposition in Virasoro characters. So these are Virasoro characters. You can think of as the trace over this module of Q to the L0 minus C over 24. No? So this statement follows from the fact that we know that Virasoro acts on this Hilbert space, and so it must decompose into irreducible representations. Yes? Ah, okay, sorry. Yes, I'm going fast because you told me that you were familiar with 2D CFTs and I didn't want to bore you, but maybe I'm going too fast and I'm losing you. Okay. So what are we after? So right now I want to essentially study symmetries of 2D CFTs, okay? In order to study them, I first need to understand how to develop some tools to play with 2D CFTs, which is what we are doing now, no? As a quick recap. So key tool, the representation of the Virasoro group, no? These are I gave you the generators, and I told you that exploiting the state operator map, the Hilbert space will be organized into irreducible modules of the Virasoro symmetry. They are highest weight modules that are defined by a condition which I erased, but I called them MCH. No? So you take a primary operator, by the state operator map, it goes to the highest weight state, and you construct all the descendants, and the descendants organize in these modules. Okay. The representations of the irreducible, they are the irreducible representation of the Virasoro of given central charge and conformal spin H. So this is a structure that because of the operator correspondence organizes the Hilbert space of the CFT on the circle in irreducible representations. Okay? So then I told you just out of that and looking at these unitarity constraints, if C, the central charge of the Virasoro algebra, if C is less than 1, no, the models are so constrained that there is a finite list of models. These are the minimal models, and their conformal weights are classified completely. No? So in particular, I gave you the values of the possible central charges for minimal models and all possible conformal dimensions of them. No? So we are solving them. Like we aren't, they have. but the thing is that these structures, these CFTs are so constrained that if you work with C less than 1 CFTs, you have all their conformal dimensions. They are given. No? And they belong to this list that I gave before. No? So in particular, if you look at them for the Ising CFT, which is the case where this M is equal to 3 and C is equal to a half, is the smallest possible C, no? You find that the possible conformal spins, the conformal dimensions that you can get, the eigenvalues of the L0 operators that you can get on these primaries have to be 0, 1/2, or 1/16. That's it for the Ising CFT. No? And both H and H bar will belong to this list. Okay. However, I haven't told you yet how to constrain their degeneracy. No, we want to understand. I mean, we know that we will have a list of operators that is labeled by by pairs of these numbers. No, but are they all populated? Not. How many there are? No, we need this information to solve for the spectrum of the theory. No, so unitarity constraints are enough to give us this list for minimal models. Of course, if the model is non-minimal, hic sunt leonens. For these ones, the Ising, we are lucky, is a minimal model, so we know everything about it. No? And now we need to constrain their degeneracies, and in order to do that, we are going to exploit locality. No? I gave a definition of what I mean by locality here, and in particular, we're going to use it for our CFT on T2. No? And the reason why I want to use it on T2 is because if you look at the partition function on T2, you can relate it to the trace in our Hilbert space. No? And if you know how to compute the trace in this Hilbert space, then you can constrain by the state operator map which primaries are realized and in which multiplicities. Okay? So what we are after is essentially what pairs of H and H bar appear here, and what are the values of these integers. These are positive integers. No? This follows because our Hilbert space is organized in irreducible representations of the Virasoro. So it's just a direct sum of irreducible modules. And for this reason, when we compute this trace, no, we obtain just products of the characters, because the L0 and the L0, sorry, this was an L0 bar, no? The L0 and the L0 bar, they commute, no? And so each of them will contribute separately a factor, which is a Virasoro character. No? It's just the trace over the representation of this. No? And so out of that, we recover this integrality constraint. Okay. And now, on top of this, in order to constrain this expression, we can use a modular invariance, no? Which is just the manifestation of locality in this context. No? Does this, was this okay? If there are still questions, I'm happy to go over them. Yes. Integrality is not integrability, it's integrality. And it is the fact that those n's are positive integers, because they are the multiplicity of the given representation of Virasoro in the circle Hilbert space. Yes, yes. How rigid are we about lunch? It's one, I can stop. And we go to lunch and we reconvene. Nobody will clear the blackboard, right?